Welcome everyone to our fourth session on analytics for managers. Today is really cool. Today we have a really fun session. Today we talk about machine learning. We talk about what is machine learning. We have a really fun use case from Stich Fix. We talk about different kinds of machine learning. So there's something that we later call supervised and unsupervised machine learning. And also we talk about the way we build these models. So we talk about the analytics process, what we do in the pre-modeling phase, then we build the actual model, so the modeling phase, and then finally, we get into production mode. So what we do in the post-modeling phase. So here are a few examples. So think about talking to an Amazon Alexa device, or you might have a speech-enabled navigation system in your car. Think what happens in the car, for example. Think about Tesla's autopilot. How does the autopilot understand what is an object that it shouldn't run into? Or how does it keep the distance? Or think about this last example here when you think about DeepL, a sophisticated translation service. So these are all examples that we use on an everyday basis. So you have some translation service that you use every day. You might have an autopilot and you might talk to a voice enabled device. And behind all these everyday technologies, there is machine learning built in. So the question is, what exactly is running in all of these different devices? In all of these examples that you see here, there is a difference between two things: the front end as a user and what is running in the back end of the technology. So often we're just using a service. We don't really think about what's going on in the back end of a service. We're just users of these technologies on an everyday basis. Think about unlocking your phone with your face, or you get recommended Word when you're writing something in Word or some other web-based editors. And these are all things that have been trained using data. Machine learning is the science of learning patterns from data. And the important part here is that they're not predefined or explicitly programmed. So when you think about it, all these examples that we had here, speech recognition, recognizing objects, or translating one set of words into another set of words, or maybe even symbols. So think about also languages that don't have characters and letters that we have here in Switzerland, but you might use symbols and Cyrillic, or you have Chinese and whatever language that is using symbols as opposed to letters. So these are all tasks where machine learning is helping us to use algorithms that mimic how we as humans learn. The bottom line is these are all things that are present on an everyday basis. And we often don't think about what's happening on our devices. Again, think of unlocking your phone. Or yes, for example, we in our house, we have a Nest doorbell and we have a face recognition service running. So that, for example, that I get a push notification when our neighbors are ringing at the door, or my wife, for example, is in front of the door. So these are all technologies where we don't really think about what's going on under the hood. But today we'll make a deep dive and better understanding what exactly is the way of how these models are trained, and also to learn about what can go wrong in the way these models are trained. There's also some demystification that I briefly wanted to talk about, because often all of the terms that you see here on the slides are thrown into the same bucket. So people talk about artificial intelligence, machine learning, deep learning. I was just a member of a PhD defense where there was also mix with AI and algorithms. But the important part here is that there are different levels and they are related to each other. But the broader field is AI, is artificial intelligence. So any technique that enables computers to mimic human behavior, in case you want to have a definition. Machine learning is one specific type of AI. It's the ability to learn without explicitly being programmed from all kinds of data sources that are inputted to a model. And there's specific techniques that we use in machine learning. So one of the super hype techniques is one form that is called deep learning. So it's learning underlying features and data, in this case, neural networks. And neural networks are on the map for decades, but deep learning is one specific form that is just a very complicated, or a somewhat more complicated neural network that has multiple layers. Don't get confused by the terminology here with layers and inputs and outputs. Just remember that AI is the broader field. Then we need to have some ability to learn from data. And that broader field is called machine learning. And then in the machine learning field, we just have different algorithms or different techniques that we use in machine learning. And one of these techniques, for instance, is deep learning. And here, for example, there's a specific case that you see here. When someone is writing the letter 313472, what we have is some model that recognizes the handwritten numbers and transforms it into something that's machine readable. And the same is going on, for example, just mapping the people that are standing in front of our house to certain labels that I give the algorithm. So that, for example, label, okay, this is my wife Sabrina. I have thousands of images that were taken when she's sitting in front of the house or when I'm sitting in front of the house. And that is something where the model simply learned over time. Okay, even though the person is sometimes wearing different clothes, it must be the same person, because every time when I label, this is my wife Sabrina, this is our neighbor Thomas, this is myself, there's one additional entry in the model that is able to create a coherent mapping of the person with the same face, often wearing different clothes. And I want to separate Christian from Sabrina from Thomas. So I label the data that we're using, but what is done under the hood is just some deep learning model that is helping us to classify different objects. So again, broader field AI, what we use to realize AI is learning from data. So that's machine learning. And then we use specific algorithms. Here in this case, for instance, deep learning. So this is simply giving us a high level representation of how we learn from data. What we have as a starting point is simply some raw data. So, and the important part about data that is often famously quoted as garbage in, garbage out. So we want to make sure that we have high quality data. And it's critical really to realize that more data is not necessarily good. So in the past, many people said, okay, let's just get more data, but more crappy data is just not making a model any better. And by the way, that's also something that's really at the forefront of research over the past, let me be very clear here, over the past few weeks. Over the past few weeks, there were multiple new fascinating papers published by the Google data science team, essentially showing that very large and complex models with billions of parameters that are learned, for example, from text data can be worse compared to relatively simple model, and simple in quotes. These are still huge models that take weeks for training. But bottom line is more data, and particularly if you have more messy data and noise, is not necessarily helping you to develop a better. So we need to think also about the data quality that we have for our then next analysis. So then when we talk about analyses, we're running a model. So in some cases, there's simply traditional analytics. And you could think of traditional analytics as running basic correlation analyses, for instance. So what is different then between a simple correlation analysis versus machine learning? Some of the more traditional methods, for example, just doing a correlation analysis or running a linear regression model, these are all models that have very strong assumptions. For example, with a correlation analysis or a linear regression, it's already in the word. You have the assumption that there's a linear relationship between the variables. So if one variable increases, the other variable should also increase linearly. Is that what we observe in reality? Probably not. In some cases, think about what is optimal in terms of advertising expenses. Maybe you have a hockey distribution that for a long period, there's just nothing happening if you're targeting the same person over and over again. But at some point, if you target the same person 20 times, maybe there's a huge spike that the person is more likely to buy the product. And that's a hockey stick distribution is something that would be very difficult to capture if you have more unusual relationships in your data using traditional methods, nonlinear relationships, and also having a huge number of variables is something that's led us to go more into machine learning over the past decades. We're still using traditional analytics, just be clear on that. But at the same time, we have more and more data. We have often very complex relationships. And a way to model these relationships, we need to rely on more sophisticated methods. In the broader field, as we talked about before, it's just labeled as machine learning. So an important part is then also when we write a model is to make sure that what we build is a good quality model. So we need to think about the way we evaluate this model in terms of the accuracy of the model. Is it reliable? So with reliability, what we essentially mean is if you run the same model multiple times, so there can be, for example, either time horizon, the model that's working today, is this same model also working in a year from now? Or do we need to update some of the relationships that we find? Because people change, right? Behavior changes. And that is a potential threat to any model that is built. So how can we make sure that we have accurate and also reliable models that we're building? And then finally, when we get into the deployment phase, so into production, how can we make sure that the models are able to be reused in industry practice? And these are just a bunch of examples. We talked before about Tesla's autopilot, or think about a voice enabled assistant, or here a few other services. Think about your weather forecast. Think about the recommendation that you're receiving on Netflix. Think about a navigation system like Waze. So these are all applications that at the core rely deeply on the ability to make sense from data, and specifically to use machine learning to build product. So the entire product is essentially built in some cases on sophisticated machine learning. If it's routing, for example, so to understand what's the fastest way to get from A to B, there's machine learning behind this. But it also, you probably realize that it gets more interesting over the past few years, because right now you sometimes have the option, not just understanding what's the fastest way to get from A to B, but you can also input some conditions. You say, okay, I don't want to get the fastest route. I want to get the route that avoids certain areas, for instance, having to pay on the auto, or you want to get the more scenic route to go from A to B. So these are all really interesting developments over the past 3 years. For example, just if you think about routing people from A to B. But the bottom line is that the process is always the same. You have some input data. We have to think about the data quality. Then we're running the model, and then we assess the accuracy and how reliable a model is. So let's unquote call this quality assurance of the model. And then finally, we get into deployment. So an interesting case here is a company called Stitch Fix. And Stitch Fix was essentially labeled as the Tinder of the fashion industry. And we come to this in a second. So what is Stitch Fix? So Stitch Fix is essentially a very cool data-driven service for getting an outfit that is recommended to you. So how do we get to these outfit recommendations? The company Stitch Fix is trying to understand your fashion tastes using data science. And for the company, it has been a competitive advantage. They said, we want to rely on data science and also having good designers and fashion experts to use data science to help people get better fashion recommendations. So what they're essentially doing is a combination of things. So initially, when you're signing up, there's a standard survey. So you want to get the sizing, you want to get some initial insight on what are certain styles that you like. You want to understand what a certain price range that you're comfortable with. And then when you have received a few recommendations and you might have also received your first package from them, they ask you in a standard survey, what are the items that you really liked? How personalized was it for you? Did it really match what you were hoping to get? Then there are so-called shuffle games. So where you see different clothing items, and that's why I said it's the Tinder of the fashion industry, where you essentially highlight, okay, I really like this item or I don't like this item. And they also augment the card data that they generate internally with additional third-party data from the brands they're working with, because they want to understand also from the data from the brands that they're selling, what are the items that work well? Where is the current trend shifting toward? So one of the exercises that we do, or that you guys are doing, is also to take a tour. So there's something that's really cool. So they put together an algorithms tour that is walking you through step by step. How are they using data science to better understand people's fashion preferences? So definitely something I highly recommend. So when you think about it, the specific way how data science here is used, in one part, you simply have the data generating process where they present you a bunch of fashion items and simply ask you, do you like item A? Do you like item B? And when you say, I like item A, that's fine. For example, take me here as a case for a sec. So I'm wearing a bluish type of shirt. It's a regular business shirt. So the question that Stitch Fix might be asking, or an algorithm tries to understand, am I the typical business shirt type of person? Maybe yes, maybe no. This is a long shirt. Do I always wear long shirts? Do I always like something that's bluish? Do I always like to have, for example, a certain style with the shirts? I don't know, slim fit or whatever. Based on these binary decisions, I like shirt A versus I like shirt B, C. They try to understand what are certain styles that you like. Is it something about the color? And that's what is depicted here on the left-hand side. So the more specific information Stitch Fix gets from my ratings, the better they understand, is there a certain color type that I really, do I want to have buttons here, or is there a certain fit that I prefer? And these are all things that can be extremely data driven, because these are all things that you can easily classify and use this as a data point to understand the person has a preference for blue colors, for a certain color type, no buttons on the collar, and so on and so forth. But, and there's a large qualifier, What is difficult for algorithms often to understand the context. So, for instance, suppose someone is saying, I'm going to this event and I know that my ex-wife will be there at the wedding or my ex-husband. I want to look sexy, but not too sexy. Something that is difficult to really put into words for an algorithm. And also the algorithm tries to understand what is your dominant fashion preferences. But a human is able to divert a little bit from that dominant fashion preference and maybe understand for a special occasion style, what exactly do you want to get? So something that is sexy, but not too sexy. That is something where a human might be able to override the recommendation that is coming from an algorithm. So that is something that Stitch Fix did really in an absolutely fantastic way. What essentially have is the initial part is all learning from people's decisions, past clothing choices, the little style games that you're playing, and then finally, when it comes to the ultimate recommendation, there's always a fashion designer looking at these recommendations and then able to tweak the model. And that is something we also talked about how UPS, for example, did the deployment. And that was a huge project over a decade where they also were working together with the drivers because they wanted to understand what are things that might inhibit that the drivers really trust into the routing recommendations that are coming from the algorithm. And the same logic applies here. Stitch Fix said from the beginning, we want to augment our fashion designers to help them develop the best recommendations for our customers. And you might be wondering now, they're all different type of predictive modeling. For example, what's the likelihood of an accident depending on the time of the day or the age of a driver? So we want to predict the likelihood that an accident occurs. And what we want to use for the prediction is the age of the driver and the time of the day. Or will customer X churn next month or default on a loan? So what is this thing that we want to predict? It's the credit default. What do we want to use as an input for prediction? Some characteristics about customers. Or how much would prospect X spend? What is the outcome that we want to predict? It's the expenses, right? What do we use as an input for the prediction? Some characteristics of the client, what the person has purchased previously. So these are all things where we have a well-defined outcome and we have a well-defined input. So what we want to understand is what is the relationship between the inputs to the output? And in other cases, and that's what we're looking here at the below part, people clustering or variable clustering. For example, we want to understand, do drivers with an accident share some similarities? Or do my customers form natural groups? What is the outcome that we want to predict? There is no outcome. We want to find similarities. So remember in the first three examples up there, the likelihood of an accident, whether there's a credit default, how much a person might be spending. These are all our outcomes that we want to predict. So we have defined outcomes in the model. We just want to understand relationships without having an outcome. So in the first case, we want to understand those people that all had an accident. What are similarities between people that had an accident? Or do I find different segments of customers? So do they form natural groups? We don't really have an outcome. What we want to get are these natural groups. Or finally, in variable clustering, you might want to do something we would call a market basket analysis. So we want to understand what items are commonly purchased together. You want to understand what's happening in the shopping basket of a person, which items form clusters, if you will. So in the upper part, when we have an outcome that we want to predict, that's what we call supervised learning. And when we do not have an outcome that we want to predict, we call this unsupervised learning. So supervised learning, when you think about it, is the way to tell the model and supervise the model, so to speak. This is what I want you to learn. I want you to learn how an accident can be predicted or a likelihood of an accident or how much someone is spending. So I want to supervise the model to learn this relationship as best as possible. With unsupervised learning, we leave it to the model to understand in an unsupervised fashion what are relationships that might be present in data. Supervised machine learning, we have a clear goal. We want to predict a target. We want to predict a target or an outcome. We use some training data to build the model where we already know the target. So that's depicted here also in the image in the lower part, where you have training data with minuses and pluses, and then you have some testing data where you want to understand, are these question marks, are these pluses or minuses? So for instance, when you have credit default, the banking industry wants to identify the likelihood of someone being at risk of credit default. So when you apply for mortgage, for instance, they're asking you about your monthly salary. They're asking you about your expenses and if you have another mortgage and so on and so forth. And you want to use that information to predict to which extent there's is a risk of a credit default in the future. The input might be the salary information, expenses, and the occupation of the person. So if they're self-employed, there might be a bigger risk that the person might be at risk of credit default because there's more uncertainty. And the different ways of doing this. So we have different methods. So we could broadly categorize them into classification and regression problems. So classification is just two different categories. For example, here the credit default example is just a class. Is the person at risk of having a credit default? Yes or no. So we just have two classes, credit default, yes or no. And in other cases, there might be a specific quantitative number we want to predict. So for example, which day throughout the week do I go for a shopping trip? That would be classification. And then also when I go for a shopping trip, how much am I paying per shopping visit? So that would be a regression problem. So we have a quantitative outcome. And then the second class that we talked about, unsupervised learning, here the goal is to segment the data into meaningful clusters or detect patterns. So the most important part here is you should just remember that there's no cluster that you want to predict or classify. What we want to find are relationships. So for example, might there be different consumer segments that we can cluster together, or are there certain items that are frequently purchased together? So that would be something that would be an association rule. So we want to understand what kind of associations do I find in the market basket of a single customer. So supervised learning, we have a clear outcome we want to predict. Unsupervised learning, we want to find relationships between the observations in the data set. So now let's talk about the analytics process. It's a fairly simple process when you think about it. We have some pre-modeling, then we do the modeling, and we have some post-modeling. The devil is always in the detail, but what we do in the next few minutes is just walk you through what is happening in each of these phases. So in the pre-modeling phase, we have to think about ways to get the data. We might have to clean the data. We might have to do some transformations of the data. So for example, you might have, I don't know, different currencies across a number of markets. So we want to all get them, for example, transformed into, I don't know, a dollar currency. So any kind of additional processing data. So when we complete the pre-modeling phase, we are getting into the modeling phase. So we have to build the model and we have to find ways to evaluate the model and the different types that you see here. So descriptive analytics, you run your measures of central tendency. So for example, what's the average expense for a customer? But if you want to go further into prediction or prescription, so into automating decisions, we're getting into the more sophisticated model building stage. So we want to build a prediction model that you say, if a customer purchased these items in the last week, there's a high chance that the customer is purchasing items in the next. Or now we have barbecue season coming. So depending on the weather, for instance, I might have the weather as an input to a model to predict what is a good time to do some price adjustments on beef on Friday, because people get into the weekend and I use the weather forecast to do dynamic pricing of the items that are sold at Miko. And then I want to understand how good is the model. So this is getting into the model evaluation part. So we want to make sure that we have not a model that is just working for the training data, but also is able to generalize and is good on predicting new cases. So that's what we call avoiding overfitting. And the way we do this is by doing something called cross-validation. I'm not getting into the technicalities here, but just that you understand there's one phase where we build the model, but then we also have to learn how can we evaluate whether this is a good model or not. And then finally, there's the post-modeling phase. So it's all about reporting. You could frame this as the analytics translation phase and getting into production. And one thing that I really liked is the way how Microsoft was highlighting that this is a dynamic process, because it looked very linear how I positioned this before. But in reality, this is a constant back and forth between at least four key areas. So you see the starting point in the upper left corner here. The first starting point is you need to start with a business understanding. You need to think about what is the problem that I want to solve. And then after that, we have to get access to data sources. And this is often broadly labeled as wrangling and cleaning the data. So data wrangling is this entire area of doing transformations and changing, for example, the original raw data. So then typically we go into the modeling phase. So we want to identify what are the most important features. And also to be clear, that there are different terminologies. So a feature or a variable or an input they all mean the same thing. It's a function of the domain. So people, for example, in computer science call this a feature. People in the social sciences call this a variable, but we all mean the same thing. So it doesn't matter if you call this a feature, an input, or a variable. So the modeling part is essentially translating the business problem into a modeling problem. And let's take the credit default example. We need to specify in the model the outcome I want to predict and the features that I use as an input for the model to predict credit default. And then finally, we have to train the model and validate how good the model is. As the last stage, there's the actual deployment. So we have to find ways to get the model into production. And there's a range of things that can go wrong between modeling and deployment stage. You want to make sure that the model is performing as it should and to which extent the results are still reliable. Because it might be the case that you learn patterns in the original model building stage that don't really generalize once the model is deployed at scale. And some I really like about the way how Microsoft was proposing this many years ago was that this is really an iterative process. The linear process we looked at before, that's nice to understand. Okay, you start with a business understanding and you get the data, you model the data, you deploy the model again. But the reality is that there's often some back and forth. And that's why we have the two arrows on each of these sides here. Because it might be the case that the business understanding was very clear, but then you go to the data acquisition and you realize you don't really get the data we were hoping to get. And you may even have to go back to the business understanding. Is this really the right kind of data that we want to have? For example, let's say a manager would be interested in understanding how satisfied their customers are. So a very simple case of customer satisfaction. So what are ways to assess customer satisfaction? There are probably a gazillion number of ways to assess customer satisfaction. So I might say the right way to do this is by assessing behavior. I want to see whether a satisfied customer will come back to our store and will buy something again. So I want to use behavioral outcomes to assess customer satisfaction. Another person might say, no, it's not just behavior, it's also the mind of a consumer. The consumer may think very positively and is super satisfied, but the person just is not coming back to the store. So we want to send them a customer survey and we just want to ask them on a scale from 1 to 10, how satisfied are you with our services? And then you have a third person saying, no, we can't just ask this scale from 1 to 10, how satisfied are you? There's already something that's called a net promoter score. Many of you have heard this, and we discussed this briefly in class, that a net promoter score is something where you have the advantage that you can create net promoter scores often within the same industry because many companies are relying on this. So it's your likelihood to recommend the service to others. But this recommendation likelihood, yes, it should be highly correlated with customer satisfaction. Am I right? Because I think you should look at behavior. Is my colleague right saying, I want to have a standard rating scale from 1 to 10? How satisfied are you with our services? And then you have a third person saying, no, we should look at something that is used in the industry using NPS scores, net promoter scores, and asking people to which extent they're willing to recommend our services. And ideally, we do all of the things at the same time. So we have some industry benchmarks. We might have also some internal own ways to assess us and hopefully also some behavioral outcomes that we measure. So few words on the pre-modeling phase. I don't really go into depth here and I just want to highlight a few critical points that you should remember. So the objective in the pre-modeling phase is really to assess to which extent the data represents a real world measure accurately. So is there any noise in the data? Do we have extreme outliers? Do we have missing values? Are there duplicates in the data? And there are just so many examples that I've seen over the years. You wonder why your mailings are not very efficient. And then you realize you have never really looked at the number of duplicates that you have. And for some people, you have 5 different addresses and essentially throwing money out of the window because you have super low individual level data about the addresses. And that happened a few times, what I've saw in the luxury industry, that they didn't carefully maintain the CRM data and had multiple accounts. And sometimes it can be true, particularly in the luxury industry, people having maybe multiple homes, but it could also be a reflection of fundamental issues that they're not constantly updating the current data. So then when they're sending out all these mailings, it's just, yeah, you're just throwing money out of the window. So bottom line here is garbage in, garbage out. So think about the data quality in the pre-modeling phase. And there can be a number of things that happen in transformation phase. So you might change the format, the structure, or even values of the data. So for instance, if you think about data integration across different markets, how do you make sure that the data is merged in the right way that you have consistently used either decimals indicated by a period or decimals indicated by a comma. Super simple things, but they can really throw up your analyses. So think carefully about the data that are conducted. And sometimes you also have to either omit data, and not all the data might be relevant for further analysis. And sometimes you also have to aggregate data because you have the sales data, for example, in some stores at the minute level, because it's very nicely tracked. And then in another store or maybe another market, you only have daily sales or hourly sales. So now you have to find the right level of aggregation that you can assess this appropriately. That for every store, you have the same level of analysis, for example, sales per day or sales per hour. So the bottom line is when we think about data, we need to think about the quality of the data. And one thing that I briefly want to point out here is missing data. Missing data can be because of a number of reasons. So either people are just refusing to answer the question, so sensitive topics. So I ask you about drug use, your expenses in certain categories, your political orientation, whether you're a religious person or not, your sexual preferences, and so on and so forth. Or in other cases, you might have missing data because what you're measuring is simply irrelevant. If you ask how happy you are with your mobile phone contract, but I'm not having a mobile phone contract. So why are they sending me these customer surveys? I'm asking my mobile experience. So these are just irrelevant questions. Or if you have a question about pregnancy experience for males, either people refuse to answer or whatever is asked is just irrelevant. So we need to think about potential biases that are problematic in what we call the data generating mechanism of how the data is created. So the bottom line is data is not a representation of objective truth. We have to think about the beliefs of the people building these data collection systems, the purposes, why they were built in the first place, and also the potential biases that are built. So what do we do in the modeling phase? Here's just one example. And that's also what you do in the practice session by using teachable machine. So we might have a classifier that we want to build. And this is a very simple classifier. We have images from four people, Laurin, Simon, Sabrina, my wife, and myself. So we took a bunch of images and built a face detection app. So we first classified what are the different categories that we want to train the model on. So we have Laurin, we have Chris, we have Simon, we have Sabrina, and then model training in the middle part. And I talk a bit more later about the epochs, the batch size, the learning rate. And then finally, we have the production. So we have the model that is simply outputting who's in the model. In this case, it's classifying Laurin a bit better than myself when we're both at the same time in the image. But that was just to play a little bit around with the model. So then the question is, what is a model? A model is just a mathematical representation of a relationship between data. In the past example, what we want to understand is what are the specific features that make this category Laurin? What are the specific facial features that make this category Sabrina? And let me quickly go back here. So the model is trying to learn, for instance, my wife Sabrina, she has some curly hair. She's blonde. Simon has dark hair. I have dark hair. Laurin has dark hair as well. And I'm wearing glasses. Simon is not wearing glasses. Laurin is not wearing glasses. And you also see there are a few caveats. We have always the same background. So it might be actually a bit of a challenge because the background is something that is also present in these images. So the model has to discriminate across all these different images for the four classes. What are the unique features that we could use to label Laurin as accurately as possible, Chris, Simon, and Sabrina? So that's what a model is doing. A model is trying to find a mathematical representation of these relationships between the inputs, in our case, the facial features of the person. For example, I'm wearing glasses to predict accurately. That must be Chris because he's wearing glasses, has dark hair, and is having a certain facial shape, for instance. So here's yet another example. So let's think about credit default. So you have some banking data. You have whether a person has a checking account, the duration that the person is as a customer, the savings information, whether the person is covering loans, what was the last loan purpose. And they want to classify to which extent that might be a very risky client. And what we have here, and that's the way how the data would be represented, we have a bunch of inputs or features that you see here by columns, the checkings account, durations, and so forth. And we have one outcome that we want to predict. And quick question to you guys, is it supervised or unsupervised learning? Exactly. It's supervised learning. Why? Because we have a well-defined outcome that we want to predict. whether the person is a risky potential bank client or not. And then for every row, so these are the inputs and outputs. So the inputs here are the first few columns, and the output is the last column, whether this is a risky client. And we have all that information per client. So we would call this an observation or a respondent or a customer, where we have for each single customer all the information across the different dimensions that we're measuring. So whether the person has a checking account, how long the person is a client with the bank, and so what we need to talk about then is, if we assess these models, we want to make sure that we get to a model that generalizes as best as possible. So we want to find patterns that predict our outcome, but we also want to make sure that we don't really fit a model to noise. So if, for example, think about the face detection apps. If the face detection app is learning very heavily what's going on in the background of the image, that's noise. And that background might change depending on the application. So the model should learn, okay, the background is irrelevant because it's not helping to discriminate, because it's the same in all the four images. So the model should be focusing on unique features that are present in the image. And that is something, you looking at the image, for you, it's clear, but a model has to learn, what are the features that help me to classify Laureen, Christian, Sabrina, and Simone. And that's exactly why we call this machine learning. The model has to learn, what are the underlying features that help me predict an outcome. And the outcome in this case is what? It's a class. It's a class of four different people. What we want to make sure then in the end is that we want to find a model that is learning these outcomes well, is not picking up noise that might be present in the background, that if the background changes, the model is still picking up the facial features of myself, right away gets it, okay, this must be Chris. So here's what we want to get at and what we want to avoid. We want to avoid either an underfitting model, and this is just a simplified class where we have two different groups that we want to predict. We want to predict either whether our observations are red or green. I don't know. Think about the credit default case. So you want to identify whether people are at risk at credit default, and you have the red colors here as these are the high risk cases, or people who actually had some credit default in the past that we use for training the data. And then we have a random selection of bank clients that never had any credit default. These are the green circles. So an underfitting model, just trying to find a linear relationship, may not be working very well. So you see that there's a lot of misclassification in the upper part. You still, among the red ones, you still have too many green ones. And among the green ones, you still have too many red ones. So there's a lot of misclassification, as we call this, present here in the underfitting. So it's a too simple model when you think about it. That's what is indicated here by the scaling and on the top. So what on the right-hand side is a model where there's too much complexity. So we have overfitting that is happening. So that's the perfect model. So in this model, as you see, every single observation is perfectly classified. All the green ones are in the green bucket. All the red ones are in the red bucket. But the model is probably too much tuned toward the current training data, and the complexity of the model is too high. So what we want to get at is, we want to get at a model that has a good balance between simplicity and complexity, and that's what in the middle part. That's a reasonable model where there is some misclassification. So you see it, you still see it's not perfect, but you can clearly see that the red ones are classified the green ones are classified very well, even though there is some misclassification. So if you want to get that model into production for a credit default risk model, that might be better compared to the left one that is suffering from underfitting and the right one suffering from overfitting. So here's just one example where on the x-axis, you see the number of nodes in a decision tree. So you could think about the number of nodes as the complexity of a decision tree. So if you only have a few nodes, you have a fairly simplistic decision tree model. If you have many nodes, so lots of different branches in a node where a model tries to predict, let's say again, credit default, you see the more complex the model gets, the lower the misclassification error. That's what's on the y-axis. And for the training data, that works better because we're getting to the perfect classification almost. So for the training data, that is done very well. But if we take new observations, so data that was never used for training the model, so we call this here a test set or validation data set, we see that there is a really interesting pattern that is emerging. So if you have an underfitting, quickly focus here on the underfitting for a second. If you have a model that is too simplistic, just a few number of nodes in the decision tree, what's happening is that the model is not picking up the relationship between some of the input variables, checking account, duration, and maybe we just have 5 variables. So this model is too simple, but the model here on the right-hand side is too complex. So there's an interesting area where you see for the training data sets, there was this constant reduction in the error. So having a more complex model really is good for the training data. But the misclassification error for the data was never used for training. So the so-called validation data set or test set, the error is going up again. So in the beginning, it's really high, and toward the end, it's really high. And there is this magic section here in the middle part where you have a somewhat complex model, but the model is picking up the most important features to be able to classify credit default risk. But we're not getting into the areas that we want to avoid as best as possible, that we have either too simplistic model, underfitting, or a model that is too complex. So speaking of overfitting on the right hand side. And what can happen? So what can possibly go wrong? So we were playing around a little bit here in this example. So what you see here is I was wearing this shirt. You see this here again in the images from myself. So I was just getting off my sweater. And I then was asking Lavine, what do you think happens if we would change clothes? He said, ah, interesting. So maybe the model is learning not just our facial expressions, because what is happening is that the model is learning these artifacts in the background. And in this case, the model thinks that this is Chris, that's 100% me, even though it's obviously Laurie, but the model was picking up on the artifact that we have learned too much of the sweater as opposed to our facial features. So the bottom line here as a final note, I really like this quote, all models are wrong, but some are useful. So then we finally get into the post-modeling phase. And in the post-modeling phase, it's all about deployment. And then something I really would like to motivate you to really do this is download the models. So when you build the model in our exercise on the teachable machine, you get a link to the model. You can save this as a JSON object. So we're not getting into the technicality, but the bottom line is you can export this model and then use it on other platforms. And a simple way to do this is to simply export a link, just send it to you by email, and then open the email on your mobile phone. For example, this was yesterday in my office, just testing it in a new environment. And voila, the model is working fairly nicely, even though the background here is different. I'm wearing a different shirt, but the original model was exclusively focusing on the facial features when we trained them. Finally, a few questions for reflection. So one of the things that you need to carefully think about is whether the data that was fed into the model is reliably and updated regularly. So the important part here is you simply want to make sure that what you built once is also working in the future, right? So you want to make sure that whatever you get as an output half a year from now is consistent with the original results. What you also want to make sure is that there is some accountability. So if you have a data science team helping you to work on an analytics project, you don't want to make this a one-off show. So you want to just give them data and say, help us to build this model. And they say, thank you, it was wonderful to work with you together, and then they're gone. So make sure that there's some accountability, that if there are some updates needed, think about the first point, that there is someone helping you to update the originally built. Third point, you need to think about who's using the model, right? This is almost a user experience type of a topic here. So if everyone is used to use Spotfire or Tableau or any kind of other typical BI tool, so any kind of other typical business intelligence tool, and all the modeling was done in a tool that only a small fraction of the people in the company are using, let's say there's a bit of a split, I don't know, 80% of the users are used to Tableau, 20% of the users are using Jump or Spotfire or any kind of other platform. And then you want to force everyone to go to the new system. That might be challenging. So you also need to think a little bit about the change management, or how can you make sure that people are actually using it, and when they're using it, they're using it appropriately. So you also need to anticipate some potential training, maybe even for people when it gets into actual production. And then finally, I really want to encourage, think also about the measurable impact on the business in economic terms, ideally, if you can, because you want to have something that is, I don't want to say defensible, but that is making a contribution to the organization. And it can be, and with economic terms, that not necessarily mean that there should be always a monetary outcome. No, not necessarily, but it should be something that is measurable and it has a downstream impact on the organization. And it can be either based on understanding what are potential risk factors that people leaving the company. And if you build a model that helps you reduce the number of employees that are leaving the company within the next half year, great. There is a clear immediate economic implication because if you have to retrain people, that's costly. The hiring process, costly. You're losing time, costly. So these are all things, even though there is not a clear, immediate monetary outcome that is in the focus, what you're having as an output has immediate business relevance. So how can you make sure that there's some downstream measurable impact on the organization? So without further ado, I'm super excited to talk more with you in our session. And yeah, enjoy playing with the algorithms tour and Stitch Fix. Enjoy working with Teachable Machine and see you soon.